Today's discussion is going to be about logs, derivatives of logs, derivatives of natural logs. But before we start getting into the derivative stuff, let's deal with what a log is and what we know about them. The answer to what we know about logs is probably not a whole lot. If we're given something in log form, like we're seeing right here, what we often had to do is convert that into exponential form. And so we're going to take the base, which is a. This is the exponent. And a to the y power is going to be equal to x. So this is probably the most important skill we're going to have. We're going to have to be able to go from log form to exponential, or if the problem is expressed as an exponential problem, we may have a better chance of solving it using log form. Now, some logs we should know. And when there's no base mentioned here, like up here there was a base of a, but down here there's no base. The base is always 10 when no base is mentioned. So 10 to the what is equal to 1? Well, that's going to have to be 0. And 10 to the what is going to be equal to 10. And so that's why our answer would be a 1. So basically what we're looking for is the exponent on the 10 that gives us this number. 10 to the what is going to give us 100. 5 to the what is going to be 125. So these come out real nicely. And even this one, 3 to the what is 1 over 27. Well, 1 over 27 is 1 over 3 cubed. So 3 to the negative 3 gives us 1/27. Because 3 to the negative third is 1/27. So looking for the exponent when we're looking for the value of a log with any particular base. These are things we should be able to figure out in our head, not have to use a calculator for. Laws of logs. The log base a of x times y is the log base a of x plus log base a of y. Now, most often we've actually gone that way with this, where we've got the sum of two logs and we've been asked, express it as a single log. We've gone that way. But let's realize that all these logs are two-way streets. So if we are given two logs and we're asked to express this as a single log, this thing would be log base 4, and we'd have to take this 32 and multiply it by the 8. And I don't know, this might come out nice. Let's double check. Let's see, that's 256. And is this a nice number or not? 4 to the what is 256. Well, 4 squared is 16. 4 to the third is 64. 4 to the fourth is 256. So that comes out real nice. Another law of logs we should know is the division. Again, we're usually going this way with it, but two-way street. Log base a of x minus log base a of y. And if we've got the difference of two logs at the same base, That's the same as a single log written as a division. Or a single log written as a division can be written as 2 logs being subtracted. So, if we do this example down here, log base 3 of 54 minus log base 3 of 2 is log base 3 of 54 being divided by 2. Or log base 3 of 27, which we know is 3. Because 3 to the third is 27. And this one right here, pretty easy one, it just allows us to bring the exponent around front. And so we could call this r log base a of x. But realize this too is a two-way street. We will oftentimes be given something in this form, and it's advantageous to us to take that coefficient and turn it into an exponent. So let's keep that in the back of our heads. I think going this way with it is what we've used most of all in the past, but being able to go the other way with it is going to be pretty important. Now natural logs. Natural logs, like natural log of 32 is equal to p. That means that now a natural log has a particular base to it, just like an log log without any expressed base has a base of 10. Natural logs always have a base of e. Don't ever have to write it there. If it's natural log, the base is e. And so what this means, as we go from log form to exponential, e to the exponent of p is equal to 32. So again, going back and forth between log form and exponential could be advantageous. Now what's a natural log of 1? In other words, e to the what is 1. Easy enough. E to the what is e. Those are logs, natural logs we should know. Those are the only two that you really are going to be required to know. Now, if we've got something like this, let's figure out what x is. Well, you think about that, and nothing really comes to mind. So again, if we're given a problem in exponential form and we aren't quite sure where to go, maybe we turn it into log form. Maybe we say, let's see, that the natural log of 10 is equal to this exponent of 7 minus 2x. Now our job is to get x all by itself, and now we got a shot at doing that. I think natural log of 10 minus 7 equals negative 2x. So if we solve this for x, x is going to equal natural log of 10 minus 7 divided by negative 2. Nice exact answer. Don't know what it is as a decimal. If it's no calculator problem, this is it. If it's a calculator problem, make sure you're accurate to 3 decimal places. So going between exponential and log form is going to be important, or exponential form and natural log form. Change of base formula used to be pretty important before calculators became so prevalent. If we were going to find the log base a of x, you'd find that by taking either the log log or the natural log of x. divided by the log log, or the natural log of a. Because our calculators back then weren't able to handle bases that weren't at 10. Well, now they can. Most of them can. But if I have a calculator, maybe I got a coal burner that doesn't do any bases other than 10 and natural log with a base of e, I guess I'd have to use change of base, and I'd have to say that this is the natural log of 71 divided by the natural log of 6. So if you have a coal burner, keep that in the back of your mind should you have to be accurate to at least 3 decimal places for some kind of a log with a base other than 10. All right, let's get into these derivatives. The derivative of the natural log of x is 1 over x. If we take a look at what natural log looks like, if you want the slope of the tangent at any point on here, we want the slope of the tangent at some point. Like right here. You want the slope of a natural log, all you've got to do is take 1 and divide it by that x value. Whatever that x value is right there, 1 over x is your derivative. And if you have an log log, it's the same thing. It too is 1 over x. But if it's an log log, what we're going to have to do is multiply that x on the bottom by the natural log of a. Just something we're going to have to memorize. All right? And actually, this one over here is the exact same thing. If I use the rule of logs, let's see, I would say that the derivative is 1 over x times the natural log of the base. Well, what is the base of a natural log? And we've already said today that the natural log of e is 1, and that's why, just say it's 1 over x. The rule is actually exactly the same, except that here we always end up with a natural log of the base that is always 1. Now things get slightly more complicated when you introduce parentheses, but when you're asked to find the derivative and parentheses are involved, what are you going to use? Yeah, from back in section 2.5, that's a chain rule. And so the derivative of the natural log of something, I'm always going to say that it is the derivative of the something divided by that something. So where I'm tempted to just say, well, it's 1 over the thing in parentheses, 5x squared minus 8x, I got to remember to multiply that by the derivative of what's inside. And the derivative of what's inside, the derivative of that something, is 10x minus 8. So I'm just going to skip this 1 over thing, and I'm going to call this the derivative of what's inside divided by what's inside. Okay, so always remember to use chain rule when you're finding the derivative of a log or a natural log. If we're doing this guy, log base 3, same thing's going to happen. The derivative is going to be the derivative of the something. It's going to be this 10x minus 8. Divided by, it's going to be the same thing, 5x squared minus 8x. But remember, when it's an log log, that we've got to multiply that denominator by the natural log of that base. So derivatives of logs, derivatives of natural logs. All right, final slide, logarithmic differentiation. Now this is kind of a complicated thing. And it isn't something that we use very often. In fact, we're only going to use logarithmic differentiation when we are told to. And you will be told to on your assignment today. Now, in order to do this, we're going to take the natural log of both sides. Both sides of the equal sign. Then we're going to find the derivative. We're going to do some implicit differentiation. That's Daft, isn't it? We're going to solve for y prime, because that's what we're looking for. Down here, if we look at the problem, the example that we're given, down here, we could quotient rule this thing. It would be a little messy, but we could quotient rule this. So there are some advantages to using this method of logarithmic differentiation. So instead of using quotient rule, we're going to use logarithmic differentiation. And the first thing we're going to do is we're going to take the natural log of both sides. So this thing is going to become the natural log of y equaling the natural log of 5x squared over 7x squared minus 4 to the third. Now, before I differentiate this implicitly, I'm going to rewrite it. I'm going to say that the natural log of y is equal to, instead of writing this as a single log, let's write this as a couple of logs. Let's write this as the natural log of 5x squared minus the natural log of 7x squared minus 4 to the third. Now, is there anything we can do with that? I mean, I can probably keep breaking this thing apart. I can call this natural log of y equaling, could I call this the natural log of 5 plus the natural log of x squared minus, could I bring this 3 around front? 3 natural logs of 7x squared minus 4. So the beauty with natural logs is you can really break this side apart and find the derivatives of some simpler terms. All right, so let's differentiate both sides implicitly. What is the derivative of the natural log of y? Well, what's the derivative of the natural log of something? Well, it's the derivative of the something divided by the something. Oh, I did make a mistake in what I wrote here. This isn't supposed to be x to the 5th, this is supposed to be x squared. All right. Now let's continue on with our derivative. And I guess what I should have done, could have very well brought that around front and called that 2 natural logs of x. So humor me and do that with me. Sorry about making that mistake on the exponent. Okay, what's the derivative of natural log of 5? Now that's a constant, and the derivative of constant is 0. What's the derivative of 2 natural logs of x? Well, 2 is a coefficient. Come along for the ride. Derivative of the natural log of x is 1 over x. Minus, now we have this coefficient of 3 coming along for the ride. And the derivative of the natural log of this is going to be the derivative of that, which is 14x, divided by this 7x squared minus 4. So now, if I want to get y primed all by itself, I'm going to give myself a little bit of room here. Here's what I want to start writing. I want to start writing 2 over x when I clean this part up. Minus, let's do what we got to do here. Well, 3 times 14x is 42x over 7x squared minus 4. And then I got to take that entire side and multiply it by this y so that I get y primed all by itself. And I'm very tempted, now I'm only doing this temporarily, very tempted to say times y. But I would like my y primed written only in terms of x. Well, if I'm going to do that, then I'm going to erase this y. I'm going to get rid of this y because in this problem, what is y equal to? And in this problem, y is equal to this, 5x squared divided by 7x squared minus 4 to the third power. Now, good news is no need to distribute that, no need to combine like terms or anything like that. If you write it like this, you have shown me that you know the method of logarithmic differentiation in your effort to find y primed, the slope of this function right up here at any particular x value. Probably going to take a little bit of practice, and you'll have the opportunity to practice as part of tonight's homework.